number 1. So when a source is moving towards an observer, I'm just going to draw a diagram to describe this. Right, so it's quite a common one. It's quite difficult to draw on this, but we just need to try our best. In fact, what we'll do, I'll change colour. That's reasonably good. Okay, so that sort of idea, the source is moving towards you, then they're going to bunch up, right, in the bit that's approaching you. So you observe an increase in frequency. So this apparent increase in frequency and when a source is moving away, then you get them spreading out. Right, so your observer was over the left-hand side of the diagram that I've drawn there. I.e. a decrease in frequency. Okay, number 2. The number 1, I should have said, actually is all about sound sources. A similar effect is observed with light. But it's usually expressed in terms of wavelength rather than frequency. So with light, it's usually expressed in terms of wavelength rather than frequency. And a source of moving away from you then will have an increased wavelength, and that's called redshift. Right, because red's at the long wavelength end of the spectrum. And number 3, although it's written in words, is actually a formula. And it says that redshift Z and notice no units So the other equation for redshift is expressed in terms of it's expressed in terms of the observed wavelength the wavelength at rest. So that's actually 3 and 5 together. Just coming. So the equations for the Doppler effect it cannot be used with light because of relativistic effects. That's why we need these other set of equations. Number 6. It's an equation that's kind of so important. It's given a name, so it's called Hubbles Law. So Hubble measured almost all galaxies were moving away from us. There are a few, but we reckon that's due to kind of local gravitational effects. There are a few moving towards us. But in the same way that you've got the planets going round stars and so on, stars going round the centre of the galaxies themselves have gravitational effects on each other. And so you might get some local clustering basically within galaxies, within which a small number of galaxies are moving towards us.
Yeah, but that, surely if you had 3 galaxies and all moving.
the simplest explanation for the fact that all the galaxies are moving away from us is that the universe is expanding. So if we assume that the Hubble constant doesn't change with time, we can estimate, sorry, it does actually say estimate, doesn't it? So using Hubble's law, we could say that the distance that any galaxy has moved since the beginning of time is v over h naught, its current speed, divided by h naught. But using a standard distance speed time calculation, we can also write that d equals vt. So we can set both of these equal to each other, and we get vt equals v over h naught. The v's cancel out, and you're left with t, the age of the universe, is 1 over h naught. Number 9. Stellar objects, so we mean stars or galaxies as well. Right, emit radiation. Basically, we're quite familiar with the idea that the sun gives out a spectrum. It doesn't just give out a single wavelength, right? And that's true for basically all stellar objects. All stellar means to do with stars. A range of wavelengths. Number 10 says that, talks about that distribution. But I think it's probably easier to draw it and then describe it. So in the learning outcomes, I'm trying to put it in words, basically. Yeah. So for example, the peak wavelength depends on the temperature of the object. And higher temperatures might result in a smaller peak wavelength. And the other thing I want to state about this graph, right, is as well as having a different peak, hotter objects emit more radiation per unit surface area at all wavelengths. So by looking at the spectra from these distant objects and finding out where they peak, then we can work out their temperature. And that's important because we can use it to estimate the temperature of the universe. So learning outcome 14 is the idea that as the universe expanded, it cooled down. And then 15 says that basically we can measure the radiation from that, just like the idea of these spectra from stars. So by measuring the peak wavelength of cosmic microwave background radiation, we can estimate the temperature of the universe There is actually a mash-up there of 15 and 16 together. So gravity is a force that could slow down the expansion of the universe. I'll talk later why I've said could there. So because of that, the ultimate fate of the universe, i.e. will it expand forever, or will it start to contract back in eventually? Oops. And it depends on how much mass, and when we do our nuclear reactions, we'll find that mass and energy are interchangeable. So it depends on how much mass and energy there is in the universe. Right? Will there be enough mass to pull it back in? 18 is the idea that current estimates of the mass and energy in the universe are uncertain. And in particular, they kind of straddle that boundary between whether it will keep expanding, right, or whether it will come back in again. So, we do not know the eventual fate of the universe. But that might change, okay, as we get more accurate measurements. And part of the reason we don't know is this idea of dark matter, so that's what the next two learning outcomes are about. And the first observation that leads to the idea of dark matter, right, is that we can estimate the mass of a galaxy by looking at how fast the stars are rotating. So the mass of a galaxy can be estimated by the orbital speeds of the stars. Basically, it requires a certain amount of force to keep them in those orbital speeds. And because we know that it's a gravitational force, we know the equation F equals gm1m2 over r squared, we can estimate then what the mass of the galaxy is. But the problem is that the estimates of the mass are much bigger than the estimates of the mass that we can actually see. So, current estimates of the mass of galaxies and by C we mean across the full electromagnetic spectrum, not just visible. So this leads to the idea of dark matter. The name given to the mass that we can't see. And then last one. Measurements of the expansion rate of the universe suggest it is increasing. Now, that doesn't really make sense, because if anything it should be slowing down because of gravity, which is why we said earlier on gravity could slow down the expansion. And this unknown then is referred to as dark energy. So this example, based on the Doppler effect, shows what happens if something's moving towards and away. So if you were standing still watching this, observer would hear the siren rise and fall in frequency. Frequency or pitch. Okay, the rise would come as it's approaching. case, the speed of the source, actually it's the same data listed in both cases. Frequency of the source is 1200 hertz, and the speed of the wave, 340 meters per second. And we'll be asked about the observed frequency, but the approaching bit then becomes, it's not in the data, but it's in what we select the equation. So you have to remember to select the minus in the bottom line from the plus or minus that's written in the formula sheet. And plug in all that into your calculator. Not getting a huge change to 3 significant figures. It would be 1220 hertz. But as the sign is moving away, same data, but this time we're selecting the plus on the bottom line. Which will give us a smaller final answer. And once again, to 3 significant figures would be 1/180. Now there are 2 equations involving redshift, and you've got to study the problem carefully to decide which one you use for which part, or sometimes you'll be expected to combine them both together in one compound calculation. But in this one, if we look at the data that we're given, we've got the rest wavelength, we've got the observed wavelength, and from that then we can work out Z. So for part A, lambda R is 589.0 nanometers, and we can stick everything in nanometers here because we're dealing with a ratio of 2 numbers. Lambda observed, 601.2 nanometers. And the formula then is Z equals lambda naught minus lambda R over lambda R. So 601.2. Plug in all your values. It's a very small redshift. I'm deliberately going to keep quite a lot of significant figures. 4 to agree with the data given is all to 4 significant figures. And Z doesn't have any units. Okay, it's a ratio. But then we can use the second equation and the next one to get the speed. For that we also need the speed of light, because the second relationship for redshift is Z equals V over C. So we can use the value of Z we've just calculated, substitute in all the values and rearrange, multiply both sides by 3 times 10 to the 8 and stick them in the 4 significant figures in this example. We get an answer for V. And lastly, we've got a worked example of Hubbles Law. In this example, we are given the speed of recession, because as we've seen from redshift, that can be fairly easily worked out. We can look up Hubbles Law, Hubbles constant, sorry. And then lastly, from that, we can get how far away the galaxy is. There's Hubbles Law in equation form. And dividing both sides by 2.3 times 10 to the minus 8 gives us D is 2.70 times 10 to 24 meters.